Okay, so in this video, we're going to be talking about informed search. And as I explained earlier in the last video, that informed search is basically telling your agent or your AI where the goal is. So you're somehow giving them the hints as to where the goal is. Also, we will be heavily using heuristics in this type of searches. What is a heuristic? Heuristic is just a hint or basically estimation as to where the goal is. Now, I have two examples. The first example is, let's assume that there are different cities. For example, city A, city B, city G, and then there is an example of a Pac-Man. But let's take a look at the cities first. So in this example, you can say that there are different cities and their heuristic or the estimation in this example is if I want to go from city A to city G, um, one possible estimation as to how far the distance would be from A to G could be calculated by using Euclidean distance. And Euclidean distance is just calculating the shortest distance from point A to point B, from the source to destination, and that is generally a straight line. Um, and the other type of a heuristic that we normally use is Manhattan distance. For example, let's say that I have an example of a Pac-Man in which this Pac-Man has to go to each of these dots, eat all of these dots, and then has to reach the goal. So in this one, instead of having a heuristic of using Euclidean distance, we specify that the Pac-Man has to go in either sideways or it has to go upwards or downwards, and it cannot go in, let's say, in a straight line. So I cannot move the Pac-Man something like this. This is not allowed. So the only way the Pac-Man can move is by moving sideways or upways, which is then would be better to use Manhattan distance instead of Euclidean distance. Now let's take a look at the first type of search that we're going to be discussing in informed search. This is known as GBFS. Let me just remove these marks and talk you through the entire traversal that we will be doing in this video. So that was H as 8, and that was, oops, there we go. Okay, so in GBFS, which is greedy best first search, and the name states that it's greedy, right? And whenever it's greedy, it will always choose something, right? Greedy means that sometimes greedy means choosing the minimum distance, sometimes greedy means choosing the maximum distance, right? Or sometimes it's some other condition, but it will always be prone to choosing that type of node or that type of information. So in this example, we will be greedy towards the smallest heuristic, right? Now in this example, I have no clue as to which heuristic might have been used, right? So the heuristic values which has been calculated, I don't know if that has been calculated using Manhattan distance, if that is calculated using Euclidean distance, or it is something entirely different. But regardless of the fact of which heuristic we use, we have these heuristic values. And GBFS purely works on heuristics only. It doesn't works on path cost. And like in UCS, the uniform cost search, we saw that we were always relying on the path, which the smallest minimum path. But in this one, we're not talking about the path, which is the reason why I have chose to ignore the path values in this example, and I've only written the heuristics. And you can see that the heuristics are written on the nodes itself. Now, how would we traverse a GBFS? Well, the way how GBFS works is first you're going to find out which is the minimum heuristic. So if you're starting with A, there's only one heuristic value to it, which is H is 8. So we're going to start with A. Now I have three options, B, C, and D. Now we're going to see which one has the least heuristic. And in this example, it's going to be B. So we go to H as equals to 1 and B. Then we're going to see which of the nodes from B has the smallest heuristic. Unlike in UCS, in which we were looking at every single node, which was every single neighbor, in this one, we're only looking towards the current neighbors of that node. And what I mean by that is once I go down the rabbit hole, I cannot go back up, which means that I cannot choose C or D any longer. And I only have two options available to me, which is either E or F. And in this case, we see that the smallest heuristic of E and F is going to be E with heuristic cost 3. And now you can clearly see the problem in greedy best first search, which is that it is not optimal and it can possibly sometimes give you the wrong path. And if you see, this also works as a badly guided DFS. It might work, right? Not always, but sometimes it will. Because you can see that you were going down the rabbit hole, you were going down some depth, and you didn't find the goal. So it's very important to know that GBFS doesn't work all the time. Now, just to give a quick recap of the difference between GBFS and UCS is that sometimes we call GBFS as an estimated cost algorithm because it's only working on heuristics, and we sometimes call UCS an actual cost algorithm because it is working purely on the path cost. But is there a way how we could combine the best of two worlds like we did in BFS, DFS, and we came with iterative deepening? Well, there is. And that algorithm is called A-star pathfinding, in which we are taking the best of UCS and the best of GBFS. We're combining both of them and creating something new. And the way how A-star works is we combine both of their functions. So UCS uses a function of minimum path cost, right? So we're putting that into G of n. And we have GBFS as the heuristic cost. So we're also adding that into the pathfinding function f. Now, also remember that UCS accumulates the distance and GBFS is not accumulating the distance. For example, in this you saw that initially 8a was 8, and then when we went down we had three options. We had h equals to 1, h equals to 8, and h equals to 2. We weren't adding the heuristic cost. So unlike in UCS, for example, if I had A and then I had B and then I had C, and this was a cost of 1, 1. When we would be traversing from A to B, we had a cost of G of n as, or let's say G of A to B as 1. And if we would be traversing from B to C, this would be a cost of 2 because we were accumulating the distance. So just note that in UCS, we are accumulating the distance, and in GBFS, we are not accumulating the heuristic cost. Now, one question would be, when are we terminating an A-star algorithm? Because in the last few searches that we did in BFS and DFS and uniform cost search and GBFS, whenever we were finding the goal, that was the point where we had to stop our algorithm. But is it always the case? So is it going to apply the same way to A-star as well? Let's see how it turns out, and let's just try to figure out what happens. So if I'm starting from A, right? So f of A would be, it would be what? The heuristic cost, which is 2, plus the path cost to get to A, and there's no path cost, so it's gonna be 0. So we go to we have a total f cost of 2, and I'm going to also create the search tree over here. So let's say I started with A and I am initially at A, and this was the smallest f of A function over here, so we would just went to A directly. Then I have two options. I can either go to B or I could go to C. So let's calculate that as well. So if I go to B, that is going to be heuristic cost of 2, and if it's C, it's going to be 1. So f of C is going to be 1, and then f, the path cost to either one of those is 2, so I'm going to add 2 to it. And then we find out that the f of B is 4 and f of C is 3. So I have two options now. I can either go to B or I could go to C, and the cost to get to A to B is now how much? 4, and to go from A to C is 3. Now, if I'm starting with A, we're going to be looking at the smallest f function. And in this one, we can see that f of c is 3. So we're going to go to C. And we then go to C. Okay, now let's try to figure out where are we going to go next. Are we going to go to B or are we going to go to G? So if I calculate my f of g over here, and while we're doing this, let's do this. Yeah, never mind. If you're doing f of g, then this is going to be how much? The heuristic cost of the goal itself is just 0 because I have reached the goal, and the path cost is now going to be accumulated. So 2 plus 3 is going to be 5. So I have this as 5, and what we see is that if I'm traversing from C to G, right, I should just terminate. Why is it that I'm calculating what is the f function of G, right? Because if I just went to G, that's it. That's finished. That's the end of story. But that's not the case, because if I had this value as 2 and this value as 3, right, the total cost to get from A to G is 5. And the value to go from A to B to G is actually 4, because that's 2 plus 2. So the path from A to B is shorter than the path from A to G. And in reality, like, we are only using heuristic cost just to figure out where the goal is. In reality, we are concerned with the actual path cost, right? And we want this to be as minimum as possible. But as we can see, if we just visited G directly, it wouldn't have given us the optimal path. It wouldn't have given us the minimum path to go from A to G, right? Which is the reason why it is very important that you would always terminate an A star search when G is dequeued from the priority queue. And if I represent this idea in a priority queue, let's say that I had, let's say there's this PQ, and we started at A, so I put A into the queue, and let's put visited as well, right? So I remove A, I put A in visited, and then I put A's neighbors into the priority queue. So I put B, and then I put C, and I say, hey, I want to go to B. The f cost of B is 4, the f cost of C is 3, so I'm going to take out C first. So I get C as visited, and I put G over here. Now I have G as 5 and B as 4. If I go to G, then that means that just means that if I put G over here, right, that just means that I visited G, but I shouldn't terminate. I should instead look out if I have any other path which is minimum. And we can see that yes, B was minimum as compared to this path of G. So we put B in visited, and we remove B, and we put that this is G of A. Let's just put as G of C, and then we have G of B. So this then turns out to be B would then have G, and this one also would have G. So this was 4, meanwhile this was 5. So we would choose this path. Now let's calculate f of G. So we did something like this. And then we would put f of G from B, and this would be how much? 2 plus 2. So 2 plus 2 would give me 4. And we can see that 4 is smaller than 5. So we would go to B to G, and we will still not end our algorithm. We would put G of B over here. And as soon, okay, so I visited G of B, I saw, is there any other smaller path? There isn't any smaller path. So I'm going to dq g of b. And as soon as I dq g of b, that is the point where I'm going to stop my algorithm. Whenever you're going to dq your goal, that is the point where you should end your algorithm. It is not the point when it is not the point where when we were actually enqueuing the goal state into our priority queue. It is when it is dequeued. Okay, so that's the difference. So when we were putting g of c, that was not the part where we had to end our algorithm. It was the part when we dequeued g of b from the priority queue. That was the point. Okay, so I hope that made sense, that whenever you are going to be using a star pathfinding, we're always going to stop a star whenever we dequeue from the priority queue, because what that ensures is that we are always choosing the minimum path, and we're also looking out for different paths which might have a smaller value of f, which we might have not considered while we were doing a star search. Okay, so you're going to terminate a star whenever your goal is going to be dequeued. Okay, so I've also written that over there. Now let's talk about why is the current A star algorithm not optimal. Like this A star algorithm is not optimal as of yet. It might seem as optimal because when we dequeued the goal G, we did figure out, hey, we did figure out the minimum path, which was from A to G with value of 2 and 2, but this is still not optimal. And the way how we're going to present it is not optimal is by giving a counterexample. And the counterexample over here is I have a very small graph, so of A nodes A, B, and G. And the way how we're going to do this is we're going to calculate the F values for all of the nodes. So I have already done that. Whoops. There we go. So the value of f of a is going to be how much? It's going to be 8 plus 0, that's 8. So we start from a. Then I have f of b as 99. Okay, this is very weird. But let's say that h is 99 over here, plus 2. So 2 is added over here, and we have f of b as 101. So I have this path, or I have this path, which is 0 plus 5. And obviously, I'm going to choose this one. And you can already see what's the problem over here. Like, the path cost over here was 5, and the path cost over here was 4. And to get from A to B to G was much more efficient and having like the least cost than it was to go from A to G directly. What was the problem over here? The problem was, one, you could say that this heuristic value was calculated in the wrong manner. It was a poor heuristic choice. But most importantly, the most important point is that you were too pessimistic while you were choosing your heuristic. And what I mean by a pessimistic heuristic is that you overestimated your shortest distance from A to G, right? You said this shortest distance from A to G could have been much lesser than 99, right? To present this idea, what I have done is I have presented a mathematical equation that your estimated cost, which was in this case 99, was greater than the actual cost, which was how much? It was 2 and it was 4, right? So your estimated cost was much more greater than the estimated cost, which led you to overestimate your heuristic, right? And what we want to do is we want to always underestimate, and we always want to be optimistic towards choosing our heuristic, right? So a good heuristic over here could have been something like, let's say, since this is h as 0, I could have chosen h as 0 as well. and there's always going to be an equals to sign over here. I'm sorry, I might have ignored that. So over here, when h is 0, I might have chosen this path instead, because now this is almost underestimating, almost equal to the actual cost, right? So this heuristic would have been much, much better than this one over here. Okay, so what is this called? This phenomena is called as admissibility. Admissibility is when we are actually keeping our heuristic as underestimated, and we're always looking at an optimistic path, which means, let's say that we have this example over here in which there is this young AI agent and it wants to go to the goal state. And what you do is, like I said, there's like this ghost, which is like telling it hints as to where it has to go. And maybe this ghost is telling this agent that, hey, you aren't going to make it, you're going way too slow, you will never make it, you'll just die over here, and you're very, very far away from the goal. And that is what is pessimistic, right? It is telling your agent that even though it might be going on the right path, but it's demotivating, right? Whereas an admissible heuristic would be that no matter where the agent is, the ghost is going to be like, hey, you're on the right path, you're going in the right direction, right? And you can do this, and yeah, you can make out of this very horrifying maze. So you would always want to be optimistic and not pessimistic in terms of heuristic. And that is always done when, okay, so one point that I would like to point out is whenever we're talking in terms of in admissibility, we do not represent our actual cost as g of n anymore. We are representing it in the form of h star n. And we can also see that if this condition is met, then you can say that your heuristic is admissible, which is that if your heuristic is greater than equals to 0, and if it is lesser than equals to the actual cost, then your heuristic is admissible. So this just states that you will always want to be underestimated. Let's try to apply this in one of the examples of 8 puzzle. Let's say that I have an 8 puzzle problem and my heuristic over here is the number of tiles misplaced, which means that, hey, if I have let's look at the number of misplaced tiles. So 7 is in the wrong position, so that's 1. 2 is in the wrong position, 4 is in the wrong position, 5 is in the wrong position, this blank is in the wrong position, 6 is in the wrong position, 8 is in the wrong position, 3 and 1, because 1 should have been over here, 2 should have been over there, and so on and so forth. So we can see that over here the heuristic cost of initial value is 8, because initially we are not doing a good job. And if our heuristic is 0, that means we are at the goal state. Is this example, is this heuristic admissible? Which means, are we underestimating to the actual cost? Well, yes, it is admissible. Why is it admissible? Well, we are underestimating because let's assume that I had this grid over here, initial and goal. So I had 1, 2, 3, 4, 5, 6, 8, 7, and then blank, and this was the goal. The misplaced tiles over here is just 2, because there's 8 is misplaced and 7 is misplaced. So my actual my current heuristic is 2, but my actual heuristic is much worse than this. My actual cost is much more worse than this, and it's because I cannot directly move 8 to 7 and 7 to 8. I have to somehow move this blank state in towards left or towards right. So for example, I've shown this next state that I've moved this blank over there, and then this blank towards the left, and then I have to somehow do some sort of an operation where this blank will go up then this will come down, and then this will then go towards the right. So there's 5 over here, blank over there, and then 8 is going to go up, right? So 8 is going to go up, then we're going to have a dash over here, then we're going to put 7 towards this dash, this is going to go here, then we're going to put the dash up there, right? So dash comes here, this comes there, and then 8 is going to go there. And you can see that this is taking a lot of steps, right? So the actual way to do this is taking a lot of steps, right? So the actual heuristic is going to be our heuristic that we just calculated is much less than what we actually want to do. So that's the reason why our heuristic is it is in fact admissible. Okay, so we could see that the difference between our heuristic and our actual cost is very big, right? Because I said that the heuristic is going to do, and clearly it's not being solved under 2 steps. So if you're using UCS, okay, so one thing that I want to point out is your A star is a form of UCS, and I did talk about this in the last video as well, that UCS is an A star algorithm is a special form of UCS, because if you have your A star is defined as f of n equals to g of n plus h of n, and if this heuristic cost turns to 0, well, you would find that your A star gets converted into a UCS, right? So it would be more advisable that you can see that if we don't have any heuristics, if you're moving more than 12 steps, it's going to take 3.6 into 10 to the power 6 moves, right? And if you're moving with an A star, if it has more than 12 steps to solve the problem, then it's going to take just 227 steps to get there. And what this means is that it's always better to have some sort of heuristic than not to have any heuristic at all. So it's very important that our A star algorithm has some sort of heuristic to it, and it is not 0. So let's take a look at a different heuristic, right? Let's say if we were trying to figure out the Manhattan distance of each of the node which was misplaced. So let's say that we had a start state of A as this one, and 1 had to be at this position, and to get 1 from over here to over there, we have to move up a Manhattan distance of 1, 2, 3. So that's 3. If I want to go if we want to move our second number tile to its correct position, which is over here, the Manhattan distance would be just 1, and so on and so forth. If you do this for all the tiles, you would figure out that your heuristic at the start is going to be 18. And now you're going to ask yourself, is it admissible? Yes, it is admissible, because again, you cannot directly move your 1 towards this correct position, because you have to some sort of use the empty space, right? And in this types of situations, right, it's always better to think your problems in a relaxed manner, which means that whenever you're thinking of heuristics, you should always be thinking as to removing the constraints. For example, the constraint over here is that you have to move your blank state to either of the tile, and then you can move, right? But when I was thinking about the heuristic, I didn't think about this constraint at all. I was just thinking of an empty board, maybe let's say it's this, and I was just saying, hey, I just want to move my 1 to its correct position, and I don't care if this constraint is being met or not, right? And similarly, when I was doing the Manhattan distance as well, I didn't care about the constraint at all, which was like I had to move this blank state so that I could get 1 to its correct position. I just assumed that maybe what I have is some sort of a way in which I can just move 1 and I can directly put 1 to its correct position. So I wasn't aware of the constraints. And that's a very good approach whenever you're thinking of heuristics, that you're often ignoring the constraints that you have. So when we are doing this heuristic, we we come to know that this heuristic is actually very close to the actual heuristic, right? And the more close your heuristic is to the actual cost, it is going to have lesser amount of steps to solve your problem, right? So the more near your heuristic is to the actual cause, the more efficient your program is going to be. Now comes the question, what if we just discussed, if my what I just discussed right now was, if my heuristic is very, very close to my actual cost, then why don't we use the actual cost in the first place, right? Well, you can't use the actual cost as a heuristic, because if you knew the actual cost of the heuristic in the first place, then you would have just solved the question, right? So what I mean by that is, the whole point of using an AI, the whole point of a search is, you don't know where the goal is, and you're trying to find where the goal is. If you knew where the goal is, then you would have just given the agent the directions right away. You would have just hard coded, right? That if it's empty, then just go right, or just go up, or just go down, and you would have just hard coded this. But you don't know where the goal is, and that's the reason why we cannot use the actual heuristic in this example. Now, can we say for sure that our heuristic at this point is A star optimal? Yes and no. If you're in if we are doing yeah if we are doing a tree search, right, in which we have some sort of a tree, let's say I have A, I have B, and I have C, and in this form, yes, your A star is optimal. But in terms of graph search, whenever we're drawing search trees for graphs, we are going to note that there can be repetitions of nodes. For example, let's say we were starting from A, we went to B, and there were two ways to get to B. So we had A to B and over here. And what this is doing is, it is bringing repetitions, right? And we saw an example of this search tree in DFS, that if you had a graph something like this, right, and this would basically lead um, this scenario would basically lead you to an infinite loop for DFS, and your DFS wouldn't work. um, and now we're gonna see that, does your A star works on cases like these as well? Well, before we discuss that, we must note that if you are creating these duplications of trees, right? This duplication which was already explored, and not even this part, I would specify that this part is more than enough, and all of this part is just repetition. Whoops, it's just repetition. um this is wasting a lot of time, it's wasting a lot of resources, right? So one way to cater that is to never expand the same state twice, and we can do that by having a set data structure, and we will be discussing how to implement a set when I'm doing the coding videos, right? And you can keep like a set of visited, in which you're like saying, hey, if A is already visited, then don't visit A again. Okay, will this type of approach will wreck completeness, right? Will it or will it not? Well, it won't, because since you're avoiding the repetitions, you're always going to be traversing that path in one way or another. And what I mean by that is, let's say that if you had a goal after C, you had a goal of G, then after every C nodes, there would be a goal G. So if you ignore the other nodes, it doesn't matter, because you would eventually get to the goal anyway. So no, it does not wreck completeness at all. Is it optimal? It is not optimal. And the reason is because, why is A star search not optimal in this case? Well, What I've done over here is I have calculated f of n as g of n plus h of n over here for each node, and I've created a search tree for it. So we can see that if we are starting with S, right, the minimum cost is 2. Then we have two options. I can choose A of 5 or B of 2. I would go over here. Now I have a C of 4 or A of 5, and I would choose this one because this is much more less than 5. Now I have a cost of 6. And over here there's a cost of 5, so I would choose this option because 5 is lesser than 6. And now I have an option of 3, which is much more lesser than G. And the first thought that would come to your brain is just go to C. But we can't do this anymore because we just defined that when we will be using a set, and that we will be keeping a set of visited, that if C was already traversed, we won't go to C again, which means that we're not going to go to this path, and we're not going to go to this path, and we're going to choose this path instead. And you can see that this path was not optimal because this one costed a value of 6, whereas this one costed a value of 5, right? And it would have been much better that if we would have chosen this path instead of this path, right? So what this means is that we cannot use this approach in A star. Whenever we're traversing a graph, we cannot use this approach of using sets. So how do we cater this problem? We cater this problem by introducing a new concept of called consistency. Consistency is local checks, and admissibility is global check. What I mean by global and local is that when I was at node B, I was globally checking the estimated cost from B to G, which means if for example, if I had a B over here, I had a C over there, I had a D over there, and then I would have my G cost, then my heuristic cost over here would be calculated checking globally towards G. And what local search does, so let me just remove this. Right, what local search does is you check your heuristic value to every other node, right? So you're not checking towards the goal itself, you're checking from one node to another. And the way how we do this is by using this formula in which we say, hey, the heuristic value of my current node minus the heuristic value of the node that I want to go to should be lesser than equals to the actual cost from the current node. So from my current node to my destination node. And the reason why there's no absolute sign is because your heuristic value over here, if you're trying to figure out the shortest distance between cities, then your heuristic value at A is going to be greater than the heuristic value of the next city, right? Because if you go to this city, then your heuristic value is going to go smaller because you're going much more nearer to a goal. And we're assuming that the goal is somewhere over there. So with this formula, we can figure out that if we would have chosen a heuristic value of 2, so I would put, a heuristic value of 4. So if I put 4 over here, minus, if I put a value of heuristic as 1 over here, this would be 3 would not be lesser than the actual cost, which is 1. And I have done that also over here as well. So 4 minus 1 is 3, which is not lesser than 1. So what that means is that this heuristic value that I've chosen for A is not good. This was a poor heuristic value because in terms of local checks or in local checks, this heuristic value should have been much more smaller than what we were using over here. So if I would have chosen a heuristic value of 2, so 2 minus 1, which is this one, if that would have been a better option because now 1 is lesser than equals to 1. So my heuristic value should have been 2 or it should have been 1 in this case. Um, so what is the effect of consistency, right? The effect is that f never decreases. And there's a proof as to how this is being done. You can look at it afterwards. I'm not going to explain this because this is very self-explanatory. But if I would just want to conclude the result, it's basically that your f value for your initial node is going to be lesser than your f value of the other node, right? So your f value is always increasing. And what that means is that as you're traversing from one node to another towards the goal, your f value is always increasing, right? And what that means is that when you reach your goal, right, when you're at this goal, the other paths have, let's say there was another path of this to here, this one would have had a much bigger f value than as compared to this one. So what that means is that once you go from A to your goal state, there might be other paths to get to G, but those f values would have been much more greater and their actual cost would have been much more greater, which means now you have basically constrained yourself that you would always have an optimal path from A to G. So just to read out what I've written over here, I've just explained this part in terms of words, that so once you go to the goal, every other path will have a higher f value, which means there is no other minimum path and you have explored the optimal path. So whenever we're talking about tree searches, we're talking about that A star is admissible. If A star is admissible, it will be optimal, but that's not the case in graph searches. And in that case, you would want to have consistency. And if you have both admissibility and consistency, then you would always have an optimal path for A star. And admissibility and consistency, one applies to another. So that was all from in-from searches. We did discuss in this video, we discussed about what was GBFS, what was heuristics. We compared GBFS with a uninformed search such as UCS. We combined an uninformed search with an informed search, a UCS with a GBFS, and we came out with A star search. And then we tried to slowly try to fix all the problems that we had with the standard A star search. And at the end, we got a very optimal way of using A star search. So that was all from this video. And in the next video, we will be talking about local searches. So without further ado, keep watching my videos. Oh my god, that was not a good way to end this video. But yeah, see you guys in the next video. Bye bye.